Now we'll go into our final presentation of this session. We'll have Radhesh Bhat from PathPartner Technologies. Radhesh is an architect with PathPartner. PathPartner is based in Bangalore, India, and they are a design services and IP company. Paul talked about safety sort of looking outside the car. That's a big, complex, multifaceted domain, as his presentation very ably illustrated. Radhesh is going to talk about safety inside the car, which is a whole other aspect to this that I think is really interesting and really promising. Radhesh?
Okay. Hello. Thanks, Jeff. My name is Radhesh Bhat, and I'm working as architect in PathPartner Technology. So, and I'd like to thank Paul as well. So, he's giving up some introduction to the safety, automotive safety. So, what I'm going to cover today is some little bit of introduction on the technology involved in drowsiness detection safety, and a little bit of introduction to the algorithms involved, not exhaustive, but some introduction. And then I'll talk about our prototype, which we have implemented on embedded processor using OpenCV algorithm. So the motivation is pretty clear. So we have been seeing a lot of accidents or a lot of things that's happening because of one of the reasons because of driver getting fatigued due to various conditions, because of various reasons, either due to maybe exhaustive monotonous driving or the night shifts, which lead to a loss of concentration and makes a danger to the life. So this is about some statistics I've collected and from the US website, NHTSA website, and then this is one part of the world, but it's happening everywhere where the automotive is concerned. So it really makes sense to have a system which monitors the alertness of a driver, and which acts as a co-pilot, and it helps the driver to save in such kind of a situation automatically. So there are quite a bit of techniques as of now it's available, but we need to see how can be deployed, which all things can be deployed. So one of the thing is physiological response of the driver, where some kind of electrodes will be connected to a driver, and then it monitors the brain signals or the heart rate. This is as such is an accurate method of determining whether a driver is fatigued or not. But as I said, it could be annoying for the driver since it's a lot of electrodes being connected, and it may not be practically feasible. Whereas there are a couple of other things, other methods, like based on the driver behavior, like or based on the posture, or based on the wheel position or the lane departure, based on that, which you can predict the fatigue detection. The other thing is based on the facial expression of the driver. So whereas the facial expression based on that, we can predict the fatigue, like based on the yawn frequency or eye blink frequency or eye gaze movement or a head movement. So in that way, computer vision is helping out here, which can become a non-intrusive or a convenient way of technique to determine whether a driver is drowsy or not. But at the same time, we need to understand the challenges or requirements when you go for a vision-based detection of drowsiness. The foremost thing is the challenging lighting conditions. So as we know that driving involves, whether it were day or night, so it involves a challenging light conditions, and then it poses a challenge to the sensors, camera sensors put on in front of the driver. And the driver wearing, especially the sunglasses, in which you may not be able to, in a normal visible light, we may not be able to detect the eyes itself. And then the driver, the pose or the head orientation during the driving, it might cause difficulty in detecting the face itself, and then hence the eyes. And it shouldn't be a disturbance to the driver, that the system shouldn't be disturbing the driver in any manner, like say a flash or LEDs, which can distract a lot. And of course, the foremost important thing is the real-time response of the system. So it shouldn't happen that after an accident you detect an alarm. Okay. So I'm talking about a simple idea, which may not be the idea, but it could be one of the idea where in which a camera can be placed in front of a driver, and it continuously monitors the state of the eye of a driver, and it determines whether the driver's eyes are closed or not, and based on the frequency or based on the state of the eye, if the eye is closed more than a normal blink period, then you alarm. So that's about. So there are quite a bit of algorithms involved in this. I would pick up very simple ones, or I would take some of the things which can be considered as a algorithm for this. So one of them could be a face detection, which can help in detecting the eyes by reducing the area of search region in the whole image. So here also there are many approaches been adopted in the recent years. So these are the available algorithms which are divided based on their type of detection mechanism. So I'm not going to cover all these algorithms. So it's up to the embedded engineer to pick up this detection algorithm based on the embedded need and based on the accuracy at which it performs. So it's a trade-off at which what application is looking at what embedded platform is looking at. So as I said, this face detection could be a starting or a first stage in your detecting the eye state. It's an optional. We can see in the next coming slides. So the next step is eye state detection, where we exploit certain properties of eye which help computer vision or embedded vision to localize the eye and then the state of the eye. So here also there are various techniques available, like shape analysis or a template matching or morphological analysis. The approaches followed could be is like you can detect an eye in already detected a face, as I said in the previous slide, where you can use a face detect region and then pass it on to the eye detection part and then detect eye. The advantage with this approach is like localizing the face region, and then hence you avoid any redundancy in the search of an eye part, and also it can help in reducing the false alarms. You know that the face is this and eyes will be part of this region, and it can become an effective in the sense since you are not searching in the whole image, it becomes computationally efficient. But the catch here is it is dependent on the face detect engine. So if the face, for any reason, if it is not able to detect, then you are losing the eye part. So that's one trade-off we have with this approach. The other approach is eye detection in the whole image. Whereas you have different techniques wherein which, based on the properties of eyes, the shape and all, you can detect the eye irrespective of the face. But again, here it could be a computationally expensive, but you don't have any dependency of the face or a face detection engine as such. So I'm going to show a couple of techniques for eye state detection. So this is one of the example where in which you can do eye state detection based on the blink and then you detect the iris, and then you do a corner detection, and then hence you track on that part onwards. So there are some more examples, but not limited to this, based on the training, and then doing the features of the image, like edge detection, and then detect the blob using Huff transforms, and then finally you detect the eye coordinate. So there is a very one of the popular algorithm which has been widely used in OpenCV is hard object detection. So this could be one of the option also, along with other in which you can utilize the same function or the same object detect function for detecting both face and eye by training both separately. So this is basically this involves basically a training and generating a classifier using HAR-like features, and then you detect a feature. You basically identify a desired object. In this case, it could be eye or a face, and then you determine the classifier by training thousands of training samples, giving positive and negative samples, telling what are the positive and what is an eye or what is not an eye, or what is face, what is not a face. And then using this classifier, use in a search window in which you can compare against the classifier, and then finally detect whether is a detected object is an eye or a face or not an eye. So as a specific, which I'm on the right side of the slide, it's an XML file in which OpenCV expects, in which you store this trainings data in the form of XML form, which contains what is the minimum window size, or how many number of stages you need to perform, and what are the weights for the classic training weights, and then thresholds, based on which it will help in detecting the object. So we need to understand a few observations about this algorithm. It's been observed that it's quite efficient in pretty high and medium light conditions, and it's been quite embedded friendly because of computationally efficient. It has shown pretty decent results. So like even in under spectacles with the normal spectacles. But at the same time, we need to understand like under very low light conditions, this may not be a reliable algorithm. But at the same time, we can address by having infrared illuminators, which can help this algorithm to detect the desired object. So this is a distance limitations. This might arise because of the search window. If you are providing more flexibility in the search window, probably you might address it in a better way. Also, there could be an issue with when the phase tilt is beyond certain angle, in which this algorithm might become inefficient. So we have taken this as an example and to show the embedded vision application as a starting point in one of the Texas Instruments DM8127 SoC. So the reason we have picked up this processor is it has got a powerful imaging subsystem. It has got a very powerful ISPs and a related subsystem. It has got a hardware face detect engine which can help her in our application. So it has got a hardware face detect engine which we can utilize, or we can offload face detection part from any CPU or DSP. It is a multi-core SoC having ARM and DSP and the related hardware engines for performing all the imaging and video processing. So it's capable of doing all 1080p video and image processing. So this example is been, as of now, is been simulated under a lab controlled environment, lighting conditions. So to take it to the next level, we are working on making it real time under driver scenario, in real-time scenario. So this goes the simple flow of the algorithm. So for the sake of algorithm flow, I have separated the face detection engine, whereas in reality, this face detection engine is part of the imaging subsystem or a capture system. So the driver video is captured and then it is fed to the face detect engine. So the face detect engine is quite fast enough to generate the coordinates, and then it's passed on to only the face coordinate is passed on to the DSP part, which DSP is a floating point 674x DSP from TI, and the eye detection part is running in DSP, which is searching for the eye state, and then based on the state driver state, it will send a signal to the display unit, and then the final alarm or the output console can be addressed by taking the output from DSP. So we are processing the face detect engine is works under QVGA resolution, whereas the capture is coming out of the 1080p, and there's a separate unit in which it goes to face detect engine. It's scaled down for the better performance, and then the DSP is also for the DSP also the video is scaled down to SIF, and then for the performance reason, and then finally the display part is given the separate link, whereas we have a synchronization between the SIF resolution and the 1080p resolution. So this is my colleague under test. So this is the result we have achieved as of now. So to make the system real time, we have done quite a bit of work both on algorithm side and system side, and also as well as DSP specific optimization side. So we have done a little bit of changes in the base OpenCV code, and then we have changed, we converted into C from the C++, and then we have changed the XML format and a little bit of redundancy in the algorithm to make suit into the constraints of embedded platform. So we had to do a floating to fixed point conversion, which boosted the performance in a pretty decent way. And then we had to do a DSP specific optimizations like pretty architecture specific optimizations like cache, where in which we make sure that the very frequently accessed data are kept in internal memory so that the cache efficiency can be increased. And we have used EDMA for our the block transfers, in the sense like we have created XML in a format of a big memory chunk, and then EDMA was used to bring that and in and out from the DDR to make sure that DSP is at least accessing the DDR. And then we have done very specific optimizations related to intrinsic instructions available in the DSP. And then we have done efficient loop, efficiently optimize the loop part of the DSP, which is the heart of the DSP performance. So DSP running at 500 megahertz and then Cortex-8 running at 600 megahertz, the improvement was quite encouraging. So initially it was just around 6 to 7 FPS of system performance. After the DSP optimization, we got into pretty much close to 24 to 28 FPS. So, and at the same time, to maintain the accuracy, we had to make sure that this extensive training of the set had to be done so that we make equivalent accuracy compared to the PC prototyping. So this was this entire setup was tested under lab environment for detecting the fatigue, and it was based on the false alarm and then the actual alarm rate, and we have pretty much observed to the accuracy of 90% without spectacles. And and we have observed 85% with spectacles. So we have to do, the next step would be to test under very low light conditions. So this is possible once we have the nearly infrared or infrared illuminators, which can help in algorithm to get a better images during night time. So that's what we have discussed is about the importance of the drowsiness detection in going ahead as an automotive safety system. And we have seen a requirement of a non-intrusive method for detecting this kind of a drowsiness system. And then computer vision is helping us in this direction to address this safety problem. And at the same time, to make it real time, we need to understand the algorithm part, the accuracy part, and then how it well suits to embedded part, so that we can get a real time and accurate system for the safety. So this is where I have taken some help from, and this is something about my company. So it's a pretty young and dynamic company. We are based out of Bangalore, and then we have in the US operations also. So we are recently got certified to ISO 9001 2008. So we are pretty much there for vision, embedded vision, for the different applications like automotive, surveillance, and consumer. So that's about it. Thank you.
Excellent. Thank you very much, Radhesh. Any questions for Radhesh? So I have, oh, yes, sir, go ahead.
From the start of your presentation, is it correct that you've decided not to address the difficult situations like dark glasses or the sun behind the driver obscuring the eyes?
We, as such, as I said in my last slide, for the night vision is one of the challenging part, right? So the night vision we are addressing by having an infrared illuminator, and for the bright sunlight, still we can address using a polarizer or a band pass filter, which can make that saturation part apart, and then helps camera to get a brighter and a better image.
What about dark glasses?
So for dark glasses, still the nearly infrared illuminator can be useful with the different wavelengths, and still it can detect the eyes out of it.
One comment. Are you planning to have a visual display as an alarm? It doesn't seem...
Visual display is the output console can be anything. It can be an alarm, or it can be a brake, control brake.
Okay.
So it could be a display as well, or it could be an audio as well.
Okay.
So,
I was just wondering if someone's
yeah,
asleep, you
it's
won't see the video.
More questions for Radhesh? So I have one for you.
Okay.
What you said 85 to 90% accurate. What level of accuracy do you think is required for something like this to be deployed commercially?
ideally 100%.
Yeah, do you think that's realistic? Is that achievable?
So possibly what I would think is possibly 100% may not be possible with this vision system. What it can be done is like some other aided vision, like lane departure or something, wheel control or monitoring the wheel, and the consistency of the wheel monitoring can help to take it to the 100% level.
Yeah, or maybe a
Head, yeah.
head pose. Yeah. Okay, very good. Any other questions for Radhesh? Okay, thank you very much, Radhesh. Very interesting presentation.